Morning. So welcome to another class on MTH418 topics in calculus. So overall today, what I want to do is I want to look at, in particular, solving linear inhomogeneous systems of differential equations. So it's the inhomogeneous, the aspect I want to focus on. So good morning to all. So if you've got any other questions, I'm happy to digress, but I might as well just start with what I've got. So I've got a picture, hopefully you can see, and hopefully you can hear me, of a mixing tank situation. So that's working. Okay. Might be good, so I can scribble all over it, just to take a screenshot. Okay. Okay. So I'll do this for the moment. If you've got any questions, please type them in and I'll do them later. So what we've got here is a tank. This is tank 1. So the tank has 100 litres in it of water, and we have another tank here. So let's assume that initially we've got no salt in this tank, so it's all just fresh water. And initially we've got, say, 2 kilograms of salt dissolved in this 100 litres of this tank. So I've got different amounts in these various two things. And so what I want to do is we've got a flushing mechanism. So we've got an intake of water coming into the first tank, so 300 litres per second. So a lot of water coming in, and we'll choose to have different concentrations of salt coming through. So, so the amount of the concentration of the salt would be some function kT over 100. That would be the concentration. And so we'll look at that in a second. So I'll think of different functions for kT in a little bit. So this is coming in fast, and what happens is we'll assume that this tank sort of dissolves the salt uniformly, so it's just uniform concentration in the first tank, but there's a mixing mechanism between the two tanks. So we've got 400 litres exiting one tank, a little bit coming back, but overall the system pushes 300 litres out the other end. So there's some sort of mixing system. And again, when we have these sort of mixing systems, you can have lots of tanks. You don't just have 2, but you only have these sort of mixing systems, then differential equations are a good way of handling it. So for example, if you want to see how, say, pollution spreads between different segments, where there's a bit of flow back and forwards, or you want to see how, say, pesticides would infect something where there is, so this might be the first one might be the tree, this might be the how much pesticides are in trees, this might be how much pesticides are in the ground, and the interaction between the two. So whenever you've got some sort of interaction, this sort of differential equation modeling is useful. So I want to see how to solve these things in a second. So let's do a few things. So we'll let, say, x, which will be a function of time, be the mass of salt in this first tank, tank 1. And yt be the mass in the second tank. So we've got 2 different, and that's what we're trying to solve for. We don't know how much salt are in both these tanks, essentially. So the concentration then, so the concentration of it, depending on which chemistry you've done, is the amount of the mass divided by the volume. So x on 100, and the concentration here is y on 100. So what I want to do then is I want to work out how does the mass of salt change in the two tanks. That's what I really want to do. So if we look at X for the moment, this is our first tank. So we've got 300 litres a second coming in, and each of these 300 litres contains a concentration of KT and 100. So if you multiply those two together, that tells you how much mass is coming in. So if you multiply those two together, you've got 3 lots of KT amount of salt coming in through the intake. Then flowing out here, you've got 400 litres a second times by the concentration. So multiply those two to give you 4x, gives you, so every second, 4 times the amount of mass of the salt is exiting out that end. So that's the rate it's flowing out. You also get some coming in, and that would be 100 litres times by the concentration of the second tank, which gives you 100 times by 100 gives you just Y. So on the other hand, for tank 2, you've got some coming in and it's leaving at 2 different places. So you've got 4x coming in. Let's make it, how would I actually fix my mistakes up? That might be useful, isn't it? So we're losing 4x every time, gaining y. So for the second tank, the stuff that's being lost from the first tank is coming in the second tank. So we're making a gain here, but we're losing y to the first tank, but then we're losing 3y just out of the system altogether. So we're losing, in the end, 4y all up. So that would be a differential, a system, differential equation system, in order to, that we're trying to solve. And we've got initial conditions, let's make initial, that initially we've got nothing in the first tank and 2 kilograms in the second tank. So that's our initial conditions that we can use for later when Charles is trying to solve various things. So I guess what I want to do is I want to look at how to solve this sort of system when KT is not 0. That's ultimately what I want to look at today, and it will be an inhomogeneous system. So if this here term is non-zero, it's inhomogeneous. If it's 0, it's homogeneous. So the way to do that first is actually to solve. So let's do case 1 super quickly. So let's do the case where it is actually homogeneous. So KT is 0. Super quickly. So if KT is 0, it just ends up being a homogeneous system, and we're getting xy dash is equal to a matrix. So -4, 1, 4, -4 times by xy. That's what the system will follow down to. And so to solve this sort of system, you work at the eigenvalues, which I'm not going to. I'm just going to tell you the answers rather than work at all the details. So you work at the eigenvalues, which is -2 and -6. You work out the corresponding eigenvectors, and they have to really match up. And they are, so from memory, 1, 2, and I should be consistent here. -1, 2 are the corresponding eigenvectors for these things here. And so once you've got the eigenvalues and eigenvectors, then the fundamental solutions would be the eigenvector times by the exponential of the eigenvalue times by t. And then so the general solution, which we'll call say YH, a little y, a little squirrel underneath it, that's our general solution, would be a constant times by this first fundamental solution plus a constant times by the second fundamental solution. So that would be our general solution for the homogeneous case. Now, I've skipped a bit of working. So in particular, you know, there's certainly a bit of working just here that I've skipped over entirely. But that just gives you the process. So just emphasizing the whole process. So now we know how to solve it in general. This is the homogeneous case. How do you solve it, the inhomogeneous one? So I've got some slides here. So a few things to mention while I think about it. Just more revision. If you look at the eigenvalues here, they're both negative. So if both eigenvalues are negative, what does that tell you about the stability of the system? So the critical point, because it's a homogeneous linear system, it tells you the critical point is going to be the origin, so x equals 0, y equals 0. So what can you say about the stability of that particular critical point? Yeah. So it tells you it's stable. So that tells you that as you let time go on, then the system will be drawn towards a stable point, i.e., after a while, all the salt will there'll be no salt in the system. So if you think back to our picture, if K is 0, if you're just putting in fresh water all the time, then the salt which is in tank Y will after a while drain out completely and you just have completely fresh water in the system. So that's pretty much what that's telling you. So not that interesting really. So you can do other things. So I've got another example, KT equals 1 and look at that sort of stuff. So I'll skip over that one. So the one I want to focus on really is this sort of example here. We'll let the incoming concentration of salt be e to the minus t on 3. And so that's the incoming concentration of salt, and therefore really want to solve the following differential equation. That's what we're really trying to solve. So this is the inhomogeneous case I want to spend some time on. So we've got xy dash is equal to our matrix from before, so minus 4, 1, 4 minus 4, xy, but what we got is an inhomogeneous term. And the inhomogeneous term, as a matter of fact, looks like this. So, and we know that at time 0, this is equal to 0, 2. So this is what we're trying to solve. So in the first case, what I solved was exactly the same thing, except this term here was just dropped out. That was what I solved before. So it's a differential equation. I'm trying to solve for x and y. And x is the concentration of the salt in the tank 1. Y is x is the mass of salt in tank 1. Y is the mass of salt in tank 2. So that's what we're trying to solve. So I'm just trying to solve for different cases for different intake concentration. So for the first case, there was no salt coming in the system at all. This time we have some salt. So I'll go back to the example. So this is the intake. So if you divide this by 100, this is the intake concentration. So you can see the concentration starts at 1 over 300, so a small amount, so a small concentration. And as time goes on, the concentration dies off. So that's pretty much what this is sort of suggesting. So I want to try to solve this sort of thing. So the way to do this is there's lots of methods, really, is what it boils down to. So lots of approaches for how to do it. So I want to show you a few of them to you. I'll show more later on. So you can even use Laplace transforms later on. So I want to illustrate a few and then talk about why would you pick one more over than the other, etc. And which one do you think is going to be easier. So at the end of the day, there's lots of choices. You're the one who's going to have to do it, so therefore you're going to be the one to choose, right? So it doesn't, in the main, so in an assignment and the exam, I will not prescribe which method you do. I'll let you make the choice yourself. But you have to make a decision about what it is. And some are better than others, depends on the circumstance, or at least in my opinion. So I think that sometimes one's better, sometimes other one's better, etc. So the first one matches probably how you've done these sort of things before, and that is called undetermined coefficients. Whatever for it. So the way, basically what the way of undetermined coefficients is we know what the solution to the homogeneous system is. I've done that already, I just mentioned it to you quickly. So all I need to do is if I can find just one solution to this one up here, I'll just ignore the definition for a moment. So just try to solve this at the top. If I can find one solution, so call it YP for a particular solution, then if I add the general one on top of it, then I pull out all solutions. And the undetermined coefficients is really just making an educated guess what the solution is going to be. So this is what it is in general, right? So how I would describe in general. So in general, you just make a guess. And you guess that what YP is in terms of whatever the thing up the top here is. So if you've got exponentials, like you've got here, so either minus t, then you guess that exponential times by some vector a, which we'll work out in a second. So that's what. So let's let G be the inhomogeneous term. So if it's got e to the minus at times by something or other, so vector v, then you're going to guess e to the minus, I should make it k. I'll be careful with not overusing letters here. So minus kt times by some other vector a. And a will be unknown, and we'll go through the system working out, which I'll do in this example. If you say you've got cos kt, or indeed if you've got sine kt times y vector, so you've got either of those, or indeed if you've got that with a exponential term at the front of it. That could be plus L or minus L. Then what we're going to do is the guesses would make is if you've got one or the other, so they'll be or, then you actually put both terms in. So if you've got cos and sines, then you'd make a guess of some vector a times by e to the minus L cos t kt plus b e to the minus L sine kt. So just taking a step back, explaining it. If the inhomogeneous bit has an exponential term in it, then we expect the actual solution to have an exponential in as well. If the inhomogeneous term had a cos or a sine in there, then we expect the particular solution to probably have both causes and sines in there. So both will probably crop up. So I've got to put them in. And so in general, so you probably expect both. Sometimes one might just disappear, which is great. So that's the sort of common things. So if G had a polynomial in there, so some sort of polynomial, just like say t term times by v, then what we're going to do is would guess p to be have a polynomial but of the same degree. So if it's a t term, we would expect t times by a, but because it's a polynomial of low degree, we might also get a constant term cropping up. And so it's this last term you might often forget. So in general, if you've got a polynomial, so say PT is a polynomial, and the degree of PT is n, then you're going to guess, a t to the n term times by a, sorry, the vector, plus a t to the n minus 1 term, etc. So you get lots of terms cropping up down to the t to the 0, which is this constant term, 0. So you're just got a constant term cropping up. So you'd expect lots of them. And again, if you've got a mix, so if you've got an exponential term and a t term, then you'd have terms for both of them put together. So the only other case that's sort of mentioned is, let's suppose that you've got lambda is an eigenvalue. So actually having lambda as an eigenvalue, and you've got g is being equal to an e to the minus e to the lambda t. So if you've got actually an eigenvalue cropping up in the exponential that comes up in the inhomogeneous term, which is not this case. So this is an example I've got here. This is in this inhomogeneous term. Then if you make the guess of just a times by e to the lambda, if that's all you did by itself, then you don't pick up everything you want to. And that's because you get some sort of conflict happening. So either lambda term already is taken into account for already, so you need to find something else in addition to that. So you still only have that term, but we chuck in another one here is when you've got repeated roots, when you've got matches, like this one here, some sort of a match happening, then you just add a t term, a t times by that as well. And that is what is in general. So if you've ever got a situation where that particular function cropping up already arises from the in the fundamental solution somewhere, then just put that term in for a particular solution, but also put the same one in with a t at the front of it. So just a polynomial of one higher order essentially in front of the term. It's the basic idea. So this is suggestion. So you can see that this method of undetermined coefficients will basically make suggestions for when this inhomogeneous term has exponentials or cos or sines or polynomials or a product of any of those. So in any of those sort of situations, it suggests what sort of patterns to look for, and you guess for what those are going to be. You can work out the solution from that. So that's when the method is going to be useful. So if this inhomogeneous term does not have any of those things, so like say a tan or a sec or something like that, then it doesn't work so well. But it works in many, many circumstances, admittedly. So you can see when it is handy and when it's not. And again, when you've solved second order difference equations, like in say 220, for example, then this is probably a poly method you've seen already, I suspect. And so since you're more familiar with it, it's the one that people often go to first, which is fine. So in this case, as I said before, we're going to guess essentially e to the minus t times by some vector a. We'll work out in a second. So what I do is I'm really going to plug it into my original equation. So my original equation here is essentially a vector y dash, so I'm going to think of yp, is equal to a matrix A times by y, something in P here, plus a vector 0, 1 times by e to the minus t. Now, when I'm doing this, just for the moment, I don't want to write an A, the actual explicit matrix over and over again. So I'll just write abbreviated form for the moment. I'll write it fully in a second. But I would like to match up equate coefficients in a little bit. And so therefore it's easier to factorize the functions of t out of the vectors. Now, in this case, it doesn't make much difference at all, really. But in other circumstances, we have several different functions of t. So you might have either minus t and a t term, for example. That is certainly helpful to have them separate. And separate them out. So I just want to do that for a simple example. So subbing in this expression, so I want to differentiate this. So differentiate with respect to time. So derivative of a is just a constant vector. So and the derivative of e to the minus t is minus e to the minus t. A y dash, well, the e to the minus t I can just a scalar, so I can just tape it right out. It says a times by a plus 1, 0 e to the minus t. So I just subbed it in. And so when I've got lots of terms, what I do is I want to equate coefficients of the various different terms. And so if you've done linear algebra, e to the minus t and e to the 2t, for example, and all different exponentials are functions which are linear independent of each other, and therefore you can just take, then you can just equate coefficients of them, so to speak. And so that the constant idea that you've seen earlier, it's the same, sort of proves the linear independence of them. So therefore we can equate coefficients of the different terms. In this case, there's only one term, e to the minus t, so it doesn't seem like a bit of much of a stretch here, but that's what you do in more general. So I've got minus a is equal to AA plus 1, 0. And that's the reason why I factorized e to the minus t term earlier, because I'll have to at some point in time. And so just bumping everything together, putting this on this side, so we're getting a plus a is equal to, and I bump that on the other side, I'm getting minus 1, 0. And again, in order to add these two terms up, I just stuck a big I in the middle here, just so I can actually add them up. And so meaning a plus I times by a is equal to minus 1, 0. And again, you might as well actually plug some things in. So a here was the matrix. So just reminding you, because we haven't written down for a while, minus 4, 1, 4 minus 4. So again, if you're doing this in your assignment, you'd have to flick all the way back up. So plugging that into here, adding on I just means adding 1 to the diagonal entries. So it'd be minus 3, 1, 4, minus 3 times by a is equal to minus 1, 0. And what we have to do is solve for little a here. Now you can do it different ways. It's just linear. It's just a linear system, and you do things like Gauss elimination, will do, etc. So for a 2 by 2 matrix, I don't know, you take your pick really. I think finding inverse is probably reasonable enough for 2 by 2. So if you had a bigger system, you might want to think differently. But so find the inverse. So let's work out the inverse of this matrix here. That'll help us out. So the inverse is going to be the 1 over the determinant. So determinant is minus 3 times minus 3, which is 9, minus 1 times by 4, which is 4, which gives you a fifth, 1/5. Then you swap the a in the d terms. So you swap the diagonal entries, which doesn't look like doing much at all, and you put minus signs in front of the off diagonal entries. And so that's the inverse, so therefore a is equal to this matrix here, inverse times by minus 1, 0. And if you multiply this out by this one here, you get 1/5. I'll leave that for the moment. Minus 3 times minus 1 gives you 3. Minus 4 times minus 1 gives you 4. That's pretty much it. And so say 3/5 and 4/5 of the two components. So what we found then is that our particular solution, so one solution for it, just one of them, is this matrix A, so 3/5, 4/5 times by e to the minus t. That's one solution of many, of course. And so I want to find the general one. So in general, the general solution would be the homogeneous part plus my particular solution I've just found out. And so from quite a bit above, so when I first intro discussion, I worked out what the solution for the homogeneous part was. So it would end up being C1, 1, 2, e to the minus 2t plus C2, what do I write down? Minus 1, 2, minus 6t. So that's the homogeneous part, and we're just adding on this new term here. So 3/5, 4/5. So that's my general solution for this particular differential equation. So what I want to do next then is to go, well, let's go back to the original question all at the top of the screen. I wanted to solve that differential equation, done that, got a general solution, but I also would like to satisfy certain initial conditions. I haven't done that yet, so I need to go back and do that. And no matter which approach you do, so this is undetermined coefficients, but you did variation of parameters or diagonalization or Laplace, well, not Laplace, but you did all the other ones, then you'll all have to resolve the initial conditions at the end, all in the same sort of way. So all the methods we do introduce so far, all of them will produce the general solution as you go through it. And so therefore you need to work out do initial conditions in the same sort of way. So what we want is at t equals 0, we've got the solution is 0, 2. So if you plug in t equals 0 into all these things here, we end up getting C1 times by 1, 2 plus C2 times by minus 1, 2 plus 3/5, 4/5. So just some tricks for how to do these things. The 3/5, 4/5 we can bear on the other side. So when you do that, you're getting minus 3/5. 2 minus 4/5 gives you 6/5. That's a constant term. Then you've got C1, 1, 2 plus C2, 1, minus 1, 2. So you really want to solve for C1, C2. That's what you're going to do. Now, the better way of doing this, I think, is in terms of using the matrices where you can. And so when you've got this sort of expression, so C1, a linear combination of different columns, then you can write the columns down as a matrix, like this. So the columns I've got, and that's multiplied by a column vector, all the different coefficients. So you can actually write those two are the same thing. That's just a convenient way of writing it down as a matrix. And when you've got this term here, then it's really just a matrix times by C1, C2 equals a constant. And the way to solve those is just, it's a linear system. So you can see it quite as a linear system, and you can do things like find inverses. So you do C1, C2, for example, then would be equal to minus 1, minus 2, sorry, this one here, inverse times minus 3/5, 6/5. And so when you've written it down this sort of way, you can easily do things like take inverses, and which is what we know when we know what C1, C2 is. So to find the inverse of a matrix, again, work at determinant. So determinant's 1 times by 2 minus 1 times 2. So 2 plus 2 is 1/4. Outside of swap the diagonal entries, so 2 and 1, put minus signs in front of the off diagonal entries. So 1 minus 2. if you don't know what some of the methods I'm doing, fire away, that's fine. So again, multiply, so you need 2 times minus 3/5 plus 1 times 6/5 gives you nothing. As a matter of fact, they just cancel out. Minus 2 times 3/5 gives you 6/5 plus another 6/5 gives you 12/5. Quarter of that would give you just 3/5. And so therefore the answer we want in this case then, so this is the solution that we have for our case, is no C1 terms, then we've got 3/5 of our next term, which was minus 1, 2, either minus 6t, plus a solution for our, plus the term which came from our particular solution, which was 3/5, 4/5, e to minus t. And therefore, that's the answer to our question, which takes a bit of work, as you can imagine. So let's just go back to explain the big picture of what we've done here. So to solve an inhomogeneous case, one option, so this is method 1, is to first find the solution for the homogeneous case. Do that separately. Then you make a guess, an educated guess, for what one other solution might be that would capture this inhomogeneous term. And you make guesses like here. So make the guess match up to the inhomogeneous term some regard. Then you plug that into the equation and solve for any unknowns you've got, which would be unknown vectors rather than unknown scalars like you've seen previously. And that's what we've done here. And once you've solved for that, then that means you recover the particular solution. The general solution is just the sum of both of them. So that idea is really important in this sort of process, and that will give you the general solution. And then if you would like to find a solution to match some initial terms or boundary condition or whatever it might be, then you plug them in to solve them. And as you can see here, since it's all a linear system, solve linear equations is sort of the heart of it all. So that's the sort of big picture of what we've done here. So knowing the solution to the homogeneous system is really important, of course. That helps you to work out what the particular solution might be in some terms as well. What does it mean? So let's just try to interpret this back into my physical situation. So remember, this is all about tanks. X is how much salt's in the first tank, Y is how much salt is in the second tank. So we have a bit of salt to begin with in tank 2, but nothing in tank 1. And what happens is we're flushing in, we're adding in some salt in the top, but a decreasing amount. So KT was equal to e to the minus t on 3. So it's going down, so it's just decreasing. So as time goes on, the salt which is in these 2 tanks will be flushed out. That's what will sort of happen. And the amount of salt in the system really is just going to be coming just from the input, which is a decreasing amount. So if we look at our answers at the bottom here, you can see that we've got one term here which matches in some regard to the salt which is there initially, and that's just getting washed out, and that's e to the minus 6t. So that's getting washed out pretty quickly, really. So in very quick terms, the salt there is disappearing, but then the salt that's being left in the system is what's coming from intake, and so that's the e to the minus t term coming in. So and because the intake salt's decreasing, the salt in the tanks is also decreasing, and so because of the mixing mechanism, we've got a certain pattern here coming. So that gives you a way of trying to physically understand. So the only way of making sure the salt doesn't all disappear, so a critical point for this system still is 0, 0. And it gets attracted to that. But what was I going to say? So in order not to get the origin as being a stable critical point, you really need to make sure that the salt coming in the system is not dying off. So keeps up, for example. So that's one method of doing this. So I want to mention some others, if possible. So method 2 is called the variation of parameters. Okay, so you've seen similar ideas to this in terms of integrating factors. So I'll just mention integrating factors and then I'll explain what it is in this circumstance. So basically how integrating factors work is if you've got a linear system, so y is equal to a linear system with an inhomogeneous term. So a key way of doing this thing is multiplying both sides by some integrating factor. Call it Z or something like that. To multiply everything by this integrating factor. Then, it should be y dash, by the way. So then when you combine, so I just chuck all the y terms one side. So when you combine these two things together, then you end up getting equal the integrating factor times by y dash. So somehow they combine together to give you a derivative of one single term is equal to zg. And so then when you do it, you go, well, fantastic. I can just, this is just a single term by itself. And so I can just integrate both sides with respect to time. That's a basic idea. And then you want to get rid of z at the end of the day. So y is equal to the inverse of the integrating factor times by the integral of z g dt. That's a basic approach for integrating factors. And you've done that when you've got a first order linear system. Not a linear system, first order linear equation. So just a linear differential equation. You've done that approach for integrating factors. And you looked at approaches for how to work them out. So that's the basic idea. For a linear system, there is just a nice way of working with integrating factor is. So the integrating factor is the inverse of the fundamental matrix. So y is the fundamental matrix. So what it corresponds to is its, so the columns are fundamental solutions. And since they're fundamental solutions, that will guarantee that y is invertible. So in this case here, so the fund solutions, and I say again, in order to do this, you need to know the solution for the homogeneous part, of course, just so you can write down what the fundamental solutions are. So you still need them, as it shows you. So the fundamental solutions in this case was 1, 2, e to the minus 2t, and 1, so minus 1, 2, e to the minus 6t. Now, you can write the fundamental solutions in different ways. I mean, so I'm not sure if you're noticing, but you could write the negative of this second one, for example, that would give you another fundamental solution. So the fundamental matrix is not uniquely defined. It doesn't matter. It still work out in the long run anyhow. So you have a little bit of choice integrating factor. And if you think back to how you did these things for second order, so first order ones, how you did it, say maths 1 and 2, I think it is, then you can change the integrating factor by any constant you want to at all. You can change, add an extra 2 everywhere, and it doesn't really change the calculation whatsoever. Same thing here is if you're just changing the constant, it doesn't make much difference. So the fundamental matrix then is pretty much just these as columns. So this one you have to combine it together. So the first column would be 1 times by e to the minus 2t, and then 2 lots of e to the minus 2t. So that's really that first fundamental solution, just that one there. The second one I'll do a different color just to make them distinct, but it's really the same matrix. It's minus 1 times e to the minus 6t, and 2 e to the minus 6t. So this is the fundamental matrix. And so pretty much what I said here is that the inverse of this pretty much is the integrating factor for this differential equation. That's pretty much what it corresponds down to. So, I mean, it looks funny. There are other different integrating factors possible. So you might see it elsewhere. You can actually write the integrating factor as an exponential of AT, actually. So it looks really neat that way. The problem is to find the that particular matrix requires a bit of work. And so it's a slightly easier one to work with is this fundamental matrix, which is a more general term, pre-multiplied by a matrix to make it look much neater, I guess. So in order to do anything with it then this is our fundamental matrix. This is what we're going to do. So the method, the details of the method is we need to find the inverse of y. It's the first step. So first step is to find y, which is a bit of effort. 2 is to find the inverse. 3 is to calculate the inverse times by the inhomogeneous part. So g in this case, okay, just to remind ourselves, is e to the minus t 0. That's what the inhomogeneous part is in this case. Then we need to integrate that with respect to time. We're just looking for a general solution, really. And so this would just be a column. So just integrating just 2 bits separately. And the last thing, to recognize the original solution, then you just do the fundamental matrix times by whatever we get from integrating. And that would be our solution. Now, if you add constants of integration in, this will give you the full general solution. If you don't bother putting constants of integration in, this will end up being just the one particular solution, and then you need to add in the homogeneous parts, just like you did before. So that's the basic idea of the process. So we found y. Let's work out y inverse and go from there. So that's y. Let's work at y inverse. Now, in case you're wondering, when is this method going to be good? So if the method of undetermined coefficients works well is if this term here has exponentials or causes or sines or polynomials or combinations thereof. So if this term here had something else in it, like tan or sec, for example, then that undetermined coefficients doesn't work so well. And so this variation of parameters works really nicely in those circumstances. So this is a more general approach I would suggest, because there's a more general integrating factor, a way of doing it. So I think this is the more general method. And again, you might prefer in the end. So let's show it to you. So to work at the inverse, you have to work out the determinant. So the determinant, let's do it more slowly. Let's do the determinant separately. So the determinant of y would be AD minus BC so if you multiply the exponential, you get e to the minus t, e to the minus 6t is both of them. So you get an e to the minus 8t cropping up in both of them. And you're getting a 2 plus 2 gives you 4 of them. So 4 e to the minus 8t is the determinant. So the inverse then is sort of 1 over the determinant, so you get e to the 8t on 4, say, times by swapping the diagonal terms, so 2 e to the minus 6t, e to the minus 2t, and putting minus signs in front of the other terms. So that's what that gives the inverse. And again, it's probably worthwhile bearing this 8 to the t in, and I just put them all together. So you're getting a half e to the 2t, a quarter e to the 2t, minus a half e to the 6t, a quarter e to the 6t. So this is our matrix here. So that's the step 2, as I said before. So step 3 is I like to work out what y inverse of G is. So I multiply this matrix by our inhomogeneous part. So just multiply the two together and you get some column vectoric. So if you multiply them together, you're getting e to the t and minus half e to the 5t in this circumstance. So as you can see, just it's good to think through the method. Whenever you do this, after this multiplication, you're just going to a column vector. And each component would just be some function of time. And so therefore what we can do is we can now integrate this column vector with respect to time. So if you integrate the first one, it's just an exponential. So we're getting half e to the t. And if you wanted to, you can put a plus c1. So you get a constant integration when you integrate. In the second term, when you integrate this one here, you're getting minus 1/10 e to the 5t. And again, if you wanted to, you could put a constant integration down. So with these constants of integration, if you left them out, as I said before, if you just dropped them out entirely, then you'd end up getting one particular solution and you add the homogeneous part at the end to recover it. If you leave them in, then it automatically adds on the homogeneous part for you automatically. So to save a bit of space, sometimes it's easy to leave them out, in all honesty. So just to recover the particular solution, I'll just cancel them out for the moment. So once you've got this particular this thing here, then to find my solution, and I've got 1p, then you just multiply the original fundamental matrix times by whatever you get here. So the original fundamental matrix was something like this. You're going to multiply it by this one here. So as I said, if we drop the C1 bits out, the constant terms out, we'll just see this part. And again, you can keep multiplying them all out, and what you get is will give you the same answer as before. Now, I'm not actually multiplying because I'm out of time. So you've got the same answer you got before. That's what will end up happening. That's why. And if you left the C1, C2, and you get the homogeneous part. So that's the basic idea of the process. And again, so over to you. You've seen both methods, and hopefully you've tried some out yourself as well already. What do you prefer? Which method of those two do you prefer for this particular circumstance? And type something. So you might say, I don't know yet. That's sufficient. Okay. Yeah. So, and again, since most people are familiar with the coefficients, and since the inhomogeneous part had just an exponential term, people are going to be rather familiar with the coefficients term. So that would, I think that, so people's comment is coefficient seems preferable, and I think that's a a sensible option in this case. So if this homogeneous part was something different, then this variation of parameters might be certainly more useful. And so you need to be prepared to do that. So there are other approaches. So you can diagonalize the original matrix. So you can diagonalize the system as well. That's another approach. So if you're going to do that sort of stuff, then I think you might as well do the variation of parameters. And that diagonalization approach only works if the matrix is diagonalizable. So if you've got repeated roots, it won't work, where this one still will. You can do other approaches still. So you can use Laplace transforms as also to solve these sort of systems. And Laplace transforms are really helpful if the inhomogeneous part here is discontinuous. And so we'll look at that later. So we won't do it now, but so we'll do that when we come to Laplace transforms in chapter 3. But even all the methods we've mentioned here, sometimes all of them end up being quite complicated if you've got if the inhomogeneous bit is discontinuous. But Laplace transforms handles that quite appropriately. You still can do it even with this approach, but it's just good to see some other things. So that's what sort of the main things I wanted to cover, and you can see it took some time to do all that, to write it all down and explain it. But I wanted to try to explain the sort of strategies as well. So some other questions I had. Someone asked about tutorial 1, question 5, and using the undetermined coefficients, and that really was the inhomogeneous part had a t in it, essentially, just a t in it. And so to guess the particular solution, I think the main thing to remember is to put the t term and a constant term, and that's the main issue, I think, to do tutorial 1, question 5. I think it's the main new part to try to work that out. So I just want to, so that might be enough information. It's only got not much time. If people want further information, the person who asked it, please fire away. So the only other question I've got, people's written down here is, so getting questions that are upside down to what I normally get, and the answer is you've probably made a mistake. So commonly when you're solving, when you're trying to find eigenvectors, then you end up getting something like something terms like a being on the top. So this term here this is be a minus lambda I. So that's what you're trying to work out. So you work out some sort of matrix. So you get a being on the top, and you get some things down the bottom here, which end up being a constant times by a and a constant times by b. That's sort of the situation you get in general. And so this is 2 by 2. So a solution to this is to change the order of these two letters. So put them in reverse order, B and A, and put a minus sign in front of one of them. So that's one particular solution. Just as that the approach I do. So maybe you're forgetting to change the order when you write down the answer. That might be what's happening. I'm not sure. So the general solution would be a constant times by all that, where t is some non-zero real number. That's what the general solution is to that, the corresponding linear system. So this is the set of all eigenvectors. This is one particular eigenvector. And so in practice, I might write down minus b and a as my first guess, but I'd simplify it down to make it look nice, whatever, from my point of view. And the question is, how do you know if you got the right answer? So maybe at this point in time, I might be giving you doubts about whether you can get the right answer or not. How can you check your answer? Well, remember, just to do it. So the matrix we had today was -4, 1, 4 minus 4, for example. And I thought, so that 1, 2 was an eigenvector. That's what I suggested. How do we know if it's actually correct or not? Just multiply them out. So if you multiply these two things out, so you're getting minus 4 times 1 plus 2 gives you minus 2 there. 4 times 1 is 4, minus 8. So 4 minus 8 gives you minus 4. Now, if things were working out properly, this should equal to the eigenvalue times by the original matrix, the original column. And again, I can factorize minus 2 out and you get what I started with. So long as we're getting A times by my eigenvector is equal to some scalar, which will be the eigenvalue, times by the eigenvector again, and that verifies it's actually working. So that's a way of checking your answer. So if you're getting it upside down, sometimes and sometimes not, just plug it, just multiply the matrix just to check your answer out. In an exam situation, okay, maybe you don't have that luxury of time. In your assignment, you certainly have you've got enough time in your hands to do that, I suggest. And hopefully that will get you at least working out if things are right or not. So any other questions that people have? Okay. So what I plan to do next week is, one, I hope you can get in assignment 1 in. If you've got any questions, fire away on the discussion boards or emails, etc. I might not give you direct answers, but all the questions so far on the discussion boards have been perfectly acceptable, so that's fine. And you can always ask. I can always just say no. So just please ask. It's better just to ask. Don't die wondering. And then next week I'll start mentioning some content for chapter 2. But all the best getting the assignment done. And as you can see, some of the working does take a bit of time, so quite a bit of space on a page. So please start sooner rather than later, which I hope you already have done. Anyway, thanks very much for your time, guys, and I'll see you next week, or I might talk to you through the week.